Section 5.3, Associations in Categorical Variables. Okay, we have two big definitions in this section, associated events and independent events. So if events are associated, if they are related in some way, and if the knowledge of one event occurring affects the probability of the other event occurring. And then independents are not associated. If two events are independent, then the knowledge that one occurs does not change the probability that the other one occurs. So what we really need to get out of this section, it's a very short section, what we really need to get out of it is when you read a situation, you need to be able to determine are those events independent or associated. So the first example here is you toss a coin 2 times in a row. So always just be thinking, I'm going to toss this coin once and I get heads, let's say, for example. Is knowledge of the fact that I got heads on that first one, does that affect whether or not I will get heads on the second one? And as long as it's a fair coin, those two things shouldn't affect each other at all. What I flip on the first one should not affect in any way what I flip on the second one. So on these, I would label that as independent. They are not related in any way. Okay, you draw a card from a deck, you keep it in your hand, and then you draw another card. So let's just say for random instance here, I draw the 2 of clubs the first time, and I hold on to that, and then I draw again. Does the fact that I drew the 2 of clubs out the first pick affect what I could choose the second pick? And yes, it does affect it in this case because I definitely am not going to pick the 2 of clubs again, right? I'm holding it in my hand, so that is out as a possibility. So it has changed the probabilities for the second draw. The fact that you're holding on to it is what makes these associated. A person's marital status and their hair color. So in these kind of instances, I always like the way that I phrase it is, if I were to have the knowledge that the next person to walk down the hallway was married, would that give me any idea about their hair color? Would I think there's a higher chance that they have brown hair or a lower chance that they have brown hair? And it shouldn't. The fact that you know one of those things shouldn't change your idea or your probability about the other one. So again, those would be independent. Same thing with person's age, and their shoe size this time. So in some cases, this may seem independent. I mean, if they're 18, is what someone says, and is that going to change what I think their shoe size is? Probably not. I'm not going to have much to go by on that one. It would be kind of a random guess. However, there is kind of a catch here, and the catch is children, when you're still growing. So if someone were to tell me that the next person to walk down the hallway is 3 years old, now all of a sudden that would change my opinion or my idea about what the probability is of them having some specific shoe size. So I would have to say on this one, associated because of kids particularly. That would give me some kind of an idea of whether or not their shoe size might be a certain thing or not. So that right there is the main bit of this section that I need you to be able to know and understand for later parts of the course. Now there is one probability rule that is generated from this, so we'll go ahead and talk about that as well. If you have determined that you have 2 independent events, then there's a formula you can use for finding the intersection, the and. If you have the probability of A and B, and they're independent, you can calculate that by doing the probability of A times the probability of B. If they are associated, then this doesn't work. So this formula only works in the case that they're independent. So all of these follow-up questions here, we can determine, first of all, that all of these are independent situations, and then we can rely on that formula. So like this first one says, suppose that 51% of all babies born in the U.S. are boys. Like as of some recent statistics, maybe there have been actually a few more boys than girls born in recent years. So then it says, what's the probability that a family planning to have 2 children will have 2 boys? So really what they're asking here is they're asking what's the probability that the first is a boy and the second is a boy. Well, children are independent events. If you have a boy first, it doesn't really tell you whether you are more or less likely to have a boy or a girl the second time around. So having more than one children are independent events. And so what that means is we can calculate this out by doing the probability of the first being a boy times the probability that the second is a boy. And this is our percentage for each one of them then. 51% times 51. That comes out as 0.2601 or about 26.01%. So there's about a 26% chance right now that a couple who's having 2 children would have 2 boys. Okay, keeping the same idea, what's the probability that if you're planning to have 2 children, you will have a boy first and then a girl? So again, that's still the idea that what you have the first time doesn't affect what you have the second time. So this one's asking what's the probability that the first is a boy and the second is a girl. So we can use that same idea, first boy times second girl. The probability of having a boy is 51%. And then the complement of that would be the probability of having a girl. So that would be 49%. Multiplying that out, we would get 0.2499 or about a 24.99% probability. So slightly less in this situation, slightly less likely that you would have a boy first and then a girl. Okay, now we're going to be talking about tossing a coin, and this time we're tossing it 3 times in a row, but we already talked earlier about sequential coin tosses are always independent. What you flip on one does not affect what comes next. So this one wants to know the probability that all 3 of them land on tails. So we're basically looking at probability of tails, tails, tails happening. Well, it's the probability of the first one being a tail, probability of the second one being a tail, probability of the third one being a tail. If it's a fair coin, every single one of these is a 50% chance. And multiplying that all out gives us 125, or it's about a 12.5% chance that you'll get 3 tails in a row. Okay, what's the probability that the first one is a tail and the other ones are heads? So what's the probability of tails, heads, heads? Again, they're all independent, so it's going to be probability of tails times probability of heads times probability of heads. But this is unique in the fact that heads and tails are the same probability. So probability of tails is 50%, probability of heads is 50%, probability of heads is 50%, and it ends up being the exact same likelihood. Still a 12.5% chance that you would do first a tail and then 2 heads. So this is a fairly short section. Those are the 2 big ideas, is that can you tell whether 2 events are associated or independent? And then if they are independent, you can use the